Okay, looks like my mic's working. If some of you can't hear me, please speak up now. All right, welcome to our third last lecture. So today we're going to be talking about relations. So that's probably the tentative calendar wrong. So did I not update it? Or do you have an old version? I'll double check that. I'll write that down. So yeah, somebody's saying the assignment is due on the 3rd. If you have an old version of the tentative calendar, maybe it says the 8th, or maybe I haven't changed it. But I'm pretty sure I did. Actually, I'm going to check that really quick. So yeah, so the tentative calendar that's up on CU Learn has assignment 4 due on the 3rd. So if you have an older version, then you have an out-of-date version. We moved it up because so that it can be marked and you guys can get feedback before the end of the semester. Okay. What else do we have to talk about? Oh yeah, the exam date is up. So let me share the screen here. It's this one, I believe. Okay, and so yeah, the official exam date's up, and we are right here. So it's from August 19th at 2 p.m. to August 23rd at 2 p.m. And I believe that's a Wednesday to a Saturday. So everybody who wants to make plans, please consult that and make sure. Assignment 4 is due. Yeah, well, I'm going to clarify that right now, actually. So the calendar has been changed. The new calendar is up on CU Learn, but if you've downloaded an older version of it, then you might have an older version of it. I'll send out a reminder for that. Assignment 4 is due on August 3rd on the civic holiday. So originally we were going to, originally it was the 8th. Originally it was here. And then we were going to move it back there so that it would have time to be marked, and then you could have feedback. You could dispute your mark if need be, but then decided to sort of compromise and have it there. So that's sort of the best compromise, so that you guys have time to argue about your grade or whatever, or deal with anything that you feel you were marked unfairly on. Yeah, Sean says I can blame it on him, but no, it's fine. It was a group decision. We tried to do what was best for you. Otherwise it's a really tight turnaround for the TAs to mark it, and then for you to get feedback before before I have to have or your marks in for well, I guess anyway, we'll it's due on the 3rd, and this is also to be fair to the TAs. Okay, so we are here today. Let's see, July 27th, and we have so 1, 2, 3 more classes. This is probably going to be review. I'll go over possibly the practice exam, which is not out yet, but I'll release one. The negative mark on tutorial 4. Yeah, so that was, so I did my best to make it fair, because if you just added every edge and there was no negative marks, then you're going to get a really good mark, and that's not what I wanted to have happen. I might revisit that and maybe take down the how much of a negative mark it is to get it wrong, but I'm not going to take away the negative mark, because then the marking is skewed. You could have just added every single edge and gotten a great mark. So that doesn't show me that you've learned anything. That doesn't show me that you know how to do the search. So yeah, the negative mark is a necessary sort of evil. It seems like most people did okay on it though. But like I said, I'll revisit it and maybe boost it a bit. I won't get rid of it, but I'll make sure that it's fair or fair enough. So I will take a look at that. Okay. And yeah, so no class next week, but the assignment is due, and there is a tutorial next week, but so tutorial 5 will be due on the Tuesday instead of the Monday, and I believe there's some adjusted TA hours to go along with that. Off the top of my head, I don't remember exactly what they are, but there should have been an email or some sort of documentation for that. And tutorial 6 is, of course, will be released that week, so you'll have to do it by the usual date. So tutorial 6 will be due the following Monday. Okay. So Sean says he hasn't given out the adjusted hours yet, but you will see the adjusted hours and be able to access the TA sort of outside of this holiday. Okay, so that's that. What else do we have? Exam date, assignment due date, last class. Yeah, so that's it for the housekeeping. Is there any other questions on any of this? So the dates and deadlines and so forth. Okay. So then we will get to the lesson. So today we're going to talk about relations. So relations are similar to functions, as you'll see. And the usual disclaimer. So these slides are by Dr. Robert Collier. I've made some modifications to them, so any mistakes you find are more than likely mine. Last week we talked about, we finished up our big O, big omega, big theta talk. So we found out 2 ways to prove big omega, big theta, and big O. One using witnesses, so that is the constants C and K. So that you need to know how to do. And then I also introduced how to prove big O using limits, and that's optional. So you can use those, or you can stick to the witnesses C and K. They're functionally basically the same. Using limits, I guess, is a little more abstract though, because you're taking the limit as something goes to infinity, so it's maybe, you know, slightly hard, the slightly higher barrier of entry to understand it. But once you do, then it's also a very useful tool. We also talked about, you can use limits instead of witnesses. Yeah, that's no problem. Just make sure you use them correctly, whatever one you decide to use. Introduction to functions. So then we looked at functions. So a function is mapping a set of inputs to a set of outputs, basically, with a few special, you know, so for each input, there's exactly one, maps to exactly one output. That's basically what a function is. And every given input must have an output. So those 2 things constrain what a function is. And we looked at function composition. So I can combine 2 functions together. I can take the output from one function and it becomes the input to the next function. We talked about injective, so that is one-to-one, surjective, which is onto, and bijective functions, which is one-to-one and onto. And so bijective function, if you recall, is simply means that I have my input set, my output set of the same cardinality, and each and I map to at most one output and at least, or each output has at most one pre-image and at least one pre-image. So yeah, that's one-to-one and onto. And we talked about invertible functions and how they have to be bijective to be invertible. So if it's not injective and surjective, then we cannot invert this function. But if it is both injective and surjective, then we can run the function backwards, so to speak. So this week we're going to talk about relations. So they're very similar to functions, but they're more permissive. So functions are sort of strict. They have those strict rules on every input must have an output, and at most one output. But relations, we sort of let some of that stuff slide. So we're going to talk about okay, yeah. So do you want to post that publicly, maybe? And then everybody can just check the chat for the hours. We'll also, you know, send out an email with the updated hours. But yeah, so maybe that's the best way to handle that. If I just say it, everybody's going to forget. Okay, so Sean posted in the chat the updated hours for that for the holiday week next week. Okay, so similar to functions, relation representation. So we're going to talk about the different ways we can represent them and sort of some of the rules surrounding them, and the properties of relations. So you know, well, you'll see what that means, and then we'll use these properties to define different types of relations. So we'll define an equivalence relation, which is you know, divides a set into equivalence classes. And we'll look at partial orders, which is, well, I mean, it has applications in, say, well, not only in just building things or any sort of task where you have to manage a large number of different paths, but also you would use partial orders for parallel programming, that sort of thing. So if you have a program that has a bunch of partial orders, so things that can be done, there are certain things that need to be done in a specific order, but others that are a bit more flexible, then you can sort of apply that to parallel programming and multi-core programming and that sort of thing. Okay, so the topic of the day is relations. So a relationship is an association that expresses how two or more entities are connected, right? So that's, of course, just a dictionary definition, so to speak. But this is our mathematical definition. So when I talk about entities, I'm talking about, of course, entities that belong to sets. So two or more, so when we say two, we're talking about binary relationships or relations. And we're going to stick to binary relations. You can have more than two sets in a relation, but we're not going to get into that in this class. So it's similar to a function, but less constrained. So an example of a relationship is taught by. So it connects me, the instructor, to each of you, the students. Right, so you can say this specific student is taught by me, etc. So some of the applications, of course, companies create online profiles of you. They can relate products that you buy and perhaps also a payment method. So, you know, you have some profile somewhere that says you bought at some point, I don't know, a new mouse with your credit card on Amazon. And so relationships can define those sort of things. Social media, so you can have, you know, you follow somebody else, or you read posts by them, or you're influenced by them. You know, maybe you like everything that somebody posts. So that's another example of relations. And, you know, of course, something topical, how you come into contact with people on a daily basis. So you ate dinner with somebody, you worked with somebody, you shopped at a certain store where other people shopped. Those are different relations that we can define mathematically, and thus, we can also apply them in a computer and, run programs on them and try and find more information or derive more information. So formally what a relation is, mathematically speaking, so we take the Cartesian product of two sets A and B. So that is the set of all possible ordered pairs of the form XY, where X is a member of A and Y is a member of B. And a relation between A and B is any subset of the Cartesian product of A and B. So a relation is a set of associations that exists between sets A and B, and technically it's defined only in one direction, from A to B in this case, but that doesn't matter. And why it doesn't matter is because if I want relations going both from A to B and from B to A, I simply define them from A union B to A union B. So the fact that they only go in one direction is really just for our purposes. You can always use this little trick to have relations going from A to B and from B to A. So that's sort of the definition. So let's get into an example. So we have a set A, which has the integers 1, 2, 3, and 4. So what is the Cartesian product, A cross A? So we took this, when did we take this? This was part of our sets. When we were looking at sets, we did Cartesian product. We didn't go into it in a whole lot of detail. All right, yeah, so if you check the chat there, Sean has given you a little more information about the hours for next week. Yeah, so we briefly looked at Cartesian products. So I map I take the from 1 to everybody, and then from 2 to everybody, from 3 to everybody, from 4 to everybody. So here I have 1 to 1, 1, 2, 1, 3, 1, 4, and then 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, etc., and then whoops, and then 4 mapped to everyone. So this A cross A is a set, and it's a set of tuples. So it's an ordered pair. And then so if I want a relation, I can represent a relation by taking any subset of this, right? So I can so maybe I get rid of some of these guys. And now this technically defines a relation. And in fact, I don't even need to get rid of those guys because a subset also includes the entire set. So this technically is a relation. So it's a set of tuples, mathematically speaking. Of course, it represents, all the things that we talked about before, but this is what we're talking about when we talk mathematically. All right, so here is all the relations that we just defined. So every tuple is represented by an arrow here. So this is the set A, which consists of 1, 2, 3, 4. And this represents A cross A, so the Cartesian product, right? So all the relations we saw before, so the tuple 1, 2 is represented by this arrow here, and so on and so forth, right? So this is just a graphical representation of the Cartesian product. And the non-simple directed version of K4. Right. So now we can take some subset of that. So we can consider the relationship conveyed by the phrase is greater than. So now we want to add some of these arrows back in to represent the relationship is greater than. So we could say that 4 is greater than 2, for instance. So then I could write this arrow back in. So that's part of the relation is greater than. We would say 2 is greater than 1, 3, etc., right? So is that clear so far? Is everybody following along, or is there any questions on any of this? Okay. So consider the relationship conveyed by the phrase is equal to, all right? So then we're gonna take some subset of this arrows that corresponds to this relation. So 1 is equal to 1, so I would draw an arrow from here to here. 2 is equal to 2, etc. Right. So then again, it should be quite simple. This is a graphical representation of the relation is equal to. And we can also, it doesn't have to be mathematical on these numbers. We can define relationships any way we want. So has a name that starts with the same letter as. So then 1 is, so 1 is related to itself. So 1 starts with the same letter as 1. 2 starts with the same letter as 2, but then we also have 3. So 2 is related to 3, and 3 is related back to 2. And everybody's related to themselves. Okay, so relationships are not just mathematical constructs. They can represent anything we like. We can also represent a relation, since it is a set, we can represent it using the set builder notation. Right, so I say R, the relation R is the tuple AB where A is greater than B. All right, so of course now, if it's not clear from the context, then I would have to perhaps define what the set A and B as belonging to some set, right? So if sometimes we omit it because it's clear from the context, but if it's not, then we could say something like this. And yeah, we're using notation from both predicate logic and set theory. But it is a set, a relationship is a set, so that's standard set builder notation. So relations combine these concepts and form part of the foundation of relational database management. So relational databases are very, very popular. They're one of the main ways that we store a lot of our information. And when you understand them, so relations in this case would now link one set of records, and you might take. So if I have some record on some profile built in some company, then they have my credit. Amazon has my credit card number, for instance, and they can point it to different products that I bought with that credit card. So these relations are part of the foundation of relational database management, which you'll take in more detail in third year. All right. So we've seen a couple ways now that we can express relations. So we're going to talk a bit more about that. So let's take the set A equals 1, 2, 3, 4, and the relation R, which relates A to itself. So we're talking about now the relation A divides B. All right. So we've talked about set builder notation. So this is the set builder notation. That's one way to represent it. We can represent it explicitly as a set, since we know it is a set. So here is 1 divides 1, 1 divides 2. So 1 divides everything, of course. 2 divides 2, and 2 divides 4. And then 3 and 4 from this set will only divide themselves. All right. We can represent it like this. So I can represent it using sort of the function diagrams that we saw before, where we represent our sets using some closed loop, and then with the items inside. And then I can draw arrows from the set, well, this is from set A to A, but basically from the input to the output, so to speak, when we were talking about functions. So then every arrow represents, so I have this arrow here, this represents 2 divides 4. We can also represent it in a matrix. So Again, I have the set I'm relating from are the rows, and the columns are the set of items I'm relating to. So if I want to represent divides, I can just fill in x's. Each of these x's is mapped to one of these arrows over here, right? So this means 1 divides 1, 2, 3, and 4. 2 divides 2 and 4. 3 divides 3. 4 divides 4. And notice it's not symmetric because relations are, they have a direction, right? So it's from one set to another. All right. So any questions on any of these representations? All right, good. Since relations are sets, we can apply all the set operations that we learned about. All right, so we can, for instance, take these two sets A and B. We take relations R1 and R2 from set A to set B. So you can see them here. And then we can combine these two relations. So we take the union of the two relations, right? So then the union is what? We want to take, does anybody remember what it is? What's the union of two sets? Yeah, so we take every element, of course, but of course they are sets. Yeah, that's in at least one of them. Since they are sets, we don't allow duplicates. So here we can see the same relation in both of these, or the same, I guess, relationship in both of these relations. So we would only put that once. And then 2x, 3x, and then 1y and 1z. Right, so that's the union. What about the intersection? What would that be? Yeah, every element they have in common. So in this case, it looks like there's only one, 1x. So that's this guy here. And then, so then set difference is, of course, I take R1 and then I do what to it? Right. So I'm going to take away all the elements in R2, but you know, this element here exists in R2. Yeah, we take out the common elements from R2. So this guy we're going to kind of ignore. Oops. And this guy we're going to kind of ignore. So we're going to take away just the first one. Okay. And we can combine them using the set builder notation and using our propositional logic operators. So we're going to build a new set using the set builder notation. So R1 union R2, what would we write here? So let's rewrite this A and B such that, so what do I take for the union? This might get complicated to write out, but how would I express R1 union R2 using this set builder notation? So we want everything that where A is greater than B, and we also want everything where A equals B minus 1. So we want both of those represented. So what's the logical operator that we put there? Yeah, that's right. So that's the OR operator. And again, we can, we want both of these But what's the logical operator now? Why not and? Yeah, it's the naming thing, right? So I said I want everything in this and in this, but that's actually an or. That's you're taking. Yeah, English is a funny language. So yeah, what's the logical operator for intersection then? And yeah, here it's an and. So what I mean here is that it satisfies both this property and this property, where here it satisfies this property or this property. So that's sort of where I'm sure everybody knows that. And what about this one then? Anybody remember how to get logically from set difference? So let's say, is there a logical operator for set difference? Or what would we do? Is it the negation of A or B? It's actually set difference is equivalent to A greater than B and the negation of this, right? So I'm going to take a shortcut. So I could have represented that logically by writing the not operator there, and then the next step, you sort of do this. But so I skipped that step. So this is set difference, right? It's R1 and not R2. All right. Good. Questions? Okay. So functions and relations are similar, but what is it that they have in common? So what is the relationship between functions and relations? So this here is, well, what is this? Is this a function or a relation? Yeah, this is a relation. So then which one of these statements would be true? So a function is a relation is a function, or they are two entirely different things. Yeah, that's right. So a function is a relation, right? So it's, if I wrote this as a function, I could write, well, let's make a really simple one. So that's a function, that's also a relation. So, but the opposite isn't true. So this is a relation, but it's not a function. So similar to functions, we can compose relations, although it's more accurate to say that functions get this behavior from relations. So for instance, we have three sets, and we can define a relation from this first set, let's call them A, B, and C, from A to B, and then another relation from B to C, and then we can use this composition notation, same as that we use for functions. So this means S follows from R, and it's equal to, if I first apply the relation R, and then I use the output of that and apply the relation S, right? So what happens here, I start with 1, and so to get this element, I first go to A, and then I follow this arrow from A to W. Now I can also get 1 to Z by going first to A, and then down to Z. And still going from 1, I can go from 1 to B, and then from B to X. Oops. Right, so that's how I get those three elements. And then I can do the same thing for 2. So each time I have to make 2 hops, and I just take all the combinations where I can start from set A and end up at set C. All right. So is that function, is the relation composition clear, or are there any questions? Okay, good. All right, so yeah, formally speaking, if we take the combination or the composition of a relation R from A to B and S from B to C, we can represent the composition mathematically by saying we have some A in the first set and C in the last set and some B in the middle, such that B links up A and C in both sets, so to speak, right? So this is the formal definition of composition. You don't really have to remember that, but it's good to see it at least once. So if I have two relations, then what is S follows R? Or R, sorry. Yeah, S follows R. So what would be, say, the first element of this set? So it's going to be a tuple 1, 0, right? 1, 0, because we start from 1, we go to 1 here, and then we look at where 1 leads to in S, and it goes to 0. So 1, 0. And then we can go, so 1 leads to 1 here, but this is the only mapping from 1 in S. So now we can look at 1, 4. So 1 goes to 4, and then we look at where 4 goes to in S, and 4 goes to 1. So, whoops. So this would be 1, 1, et cetera, et cetera. So then if we did that for all of them, so 2, 1, so 2 goes to 3, and then 3 goes to 1. 2 goes to 3, 3 also goes to 2, so that's where I get these two elements. 3 goes to 1, 1 goes to 0, and 3 goes to 4, and 4 goes to 1, so we got this guy. So that's the composition of those two relations. We can also compose a relation with itself. And we can express that using the shortcut. So if we have a relation R, if we say R composed with R, we can say R squared. Right? And so then if we have R composed with R composed with R, we have R cubed, and so on and so forth. So if we had this relation R, this would be the first, R to the first, this would be R squared. So to get to R squared now, I go from 1 to 1, and then, well, 1 leads nowhere. Is that right? Maybe that might be a mistake there. So 2 to 1 goes, so 2 to 1, I map from 2 to 1, and then from 1 back to 1. Oh, yeah. Yes, that's correct. Sorry. Yes. So technically, I was looking at this. Never mind. So technically, we just, if we write this set out twice, you could do that. But yeah, 1 leads to 1, and then 1 leads to itself. Yes, so that's there. 2 leads to 1, and then 1 leads to 1. 3 leads to 2, and then 2 leads to 1. So we got this guy. And then 4 leads to 3, and 3 leads to 2, so we have this guy. And we can compose it again. So we can compose R to the 1 with R squared, and we get 1 goes to 1, and then 1 goes to 1 again. So we have this guy. 2 goes to 1, and then 1 goes to 1, so we have this guy. 3 goes to 2, 2 goes to 1, and 4 goes to 3, and 3 goes to 1, et cetera. And then at this point, so if we compose R cubed with R1, we get the same set over again. So we get 1 goes to 1, and then 1 goes to 1 here. 2 goes to 1, and then 1 goes to 1 here, so we get 2, 1 again. 3 goes to 2, 2 goes to 1, so we get 3, 1. And 4 goes to 3. And 3 goes to 1, so we get 4, 1. What happens when it references a pre-image that isn't defined? Then it just goes nowhere, right? So you mean that in the second relation, so we actually have that here, right? Or do we? 4, 3, 3, 2. Yeah, it just would go nowhere at that point. That's, as far as I know, that's perfectly okay. Even though we're not showing it explicitly here, you can have sort of dangling relationships that go nowhere from, if we're saying S follows R, then we could say that, you know, in R I have the relationship 1, 2, but in S, nothing starts with 2. So then this relation goes nowhere. That's fine. Okay. Any other questions on this relation composition? And then, interestingly enough, when we're composing the relation with itself, you know, r to the 4th equals r cubed, r to the 5th. As many times as I want to compose it after that, it's going to stay the same thing in this particular case. Okay. All right, so let's talk properties of relations. That's right. If it goes nowhere, then you don't include it. So it has to be specifically, so if we look back at the definition, so what you guys are asking about is this case here. So we need this, there exists B element of B. So this is, again, a relation from set A to set B to set C. So specifically to compose it, every element that we find in this composition, there has to be some linking element in, some linking element in the set B. So if I go from A to B and then I map some element that doesn't map to C, then that's not going to give me any element in my final composed set. All right. Okay. All right, so now we're going to talk about different types of relations, different properties of relations. So if R is a relation on A, then we say R is a reflexive relation if for all the elements in A, we map that element to itself in the relation, right? So an example of that is equal to, is that relation reflexive? Well, if we think about it, yeah. So we're going to look at these examples. So what do we think? Is equal to a reflexive relation? Yeah. So that's probably one of the simpler ones. So it's reflexive if every element maps to itself. So is equal to, the only relation it has is that every element maps to itself. So in fact, it is reflexive. What about is greater than? Is it reflexive? Yeah. So is greater than is not reflexive. So in this case, nothing maps to itself. We have no elements like this. So is greater than is not reflexive. Let's look at our A divides B, but now we're going to look at some of our other formats. So is divides a reflexive relation? Yes. And how we know that is we have these X's down the diagonal, right? So if we look at the matrix representation, then it's pretty clear to whether or not it's reflexive just by looking at it. Okay, so that should be pretty straightforward. If R is a binary relation on A, then R is called a symmetric relation if for all x and y that are in the set A, if xy is in the relation R, then yx is also in the relation R, right? So again, we're going to look at our 3 examples. So what about is equal to symmetric? Yeah, it technically is, right? Because for instance, 1, 1, if I reverse those 2 elements, that item exists in that relation. So yeah, in this case, is equal to a symmetric because 1, 1 in R implies that 1, 1 is in R. That's a tautology. Is greater than. So is that symmetric? So if xy is in R, is yx in R? That's no, that's correct. So for it to be symmetric, I would have to have these other arrows, right? So every time I had an arrow from 4 to 2, for instance, I would have to have one back from 2 to 4. So in this case, the relationship is not symmetric. What about divides? Is that symmetric? No. And again, with the matrix representation, it's, you know, somewhat easier to see because if it's symmetric, it's a symmetric matrix. So if I had, say, where am I? 3, 1, 3, 1. If I had, then I need this guy. So if I had these x's, then it would be symmetric. It could just, if I can reflect it along the diagonal, then it's a symmetric matrix, and it's also a symmetric relation. So divides is not symmetric. Yeah, and so this is sort of an example that does sort of go with what I showed you before. So let's say that the sets are slightly larger if I had the numbers from 1 to 5, and my relation is A starts with the same letter as B, then I do get this symmetric relationship, right? So if 2 starts with the same letter as 3, then 3 also starts with the same letter as 2. And if 4 starts with the same letter as 5, then 5 starts with the same letter as 4. So that's just another example showing you how to identify the symmetric relation on the matrix. All right. So now what is an anti-symmetric relation? So if I have x and y that are in the set A, then xy being a member of R and yx being a member of R implies that x equals y. All right. So let's see what this means with our 3 examples. So does this fit the description of anti-symmetric is equal to? Yeah, right. So because if x and y, if xy and yx are there, then x equals y, and that's the case here. So I'm allowed to have this sort of symmetry as long as it's along the as long as it's mapping a thing to itself. So is equal to is anti-symmetric. What about is greater than? Is that anti-symmetric? Yeah, it's anti-symmetric because I don't have arrows going both ways with these relations. So I have only, in this case, I don't have the, if I have the arrow from 4 to 2, then I don't have the one back from 2 to 4. But I'm allowed to have, you know, these guys, but I don't, so. And A divides B, is that anti-symmetric? Yeah. And how I can tell is, well, I'm allowed to have these guys along the diagonal, but otherwise I don't have any of these guys reflected along the diagonal. So the matrix is not symmetric at all for it to be anti-symmetric. Although I could have, say, we don't see it here, but if I had a relation here, that's fine because I don't have the corresponding one here. So, you know, it's not just that I only have elements in the matrix representation above the diagonal. They can also be below as long as none of them are reflected. Starts with the same letter as. Is this anti-symmetric? No, right? And that's simply because you can see right away that I have these reflected elements that are not along the diagonal. And I only need one. So it could have been, I could have had this. So I have sort of an anti-symmetric element, but as long as I have one example of symmetry, then it's not anti-symmetric. All right, does that make sense? Hopefully. Oh, oops, I think I got an extra slide mixed in there. So if R is a binary relation on N, then can R be anti-symmetric and symmetric at the same time? So I want to have these two properties. I want this symmetric property and the anti-symmetric property. So what would that relation look like if it exists? Or does it exist? Yeah, is equal to, yeah, every element to itself, right? So I'm allowed to have this. This is symmetric and anti-symmetric at the same time. So the is equal to relation is symmetric and anti-symmetric. Good. All right, so we've talked about reflexive. Is a relation with no elements also valid for that? For these properties, you mean? What do you think? So how would we prove it? So yeah, so let's say I had a relation, that's the empty set. Yeah, I mean, it is since a relation is a set, it can be the empty set. And is this, for instance, symmetric? Yeah, it is symmetric because, and that's the, what is it called? What's that? Vacuous proof. Vacuous or trivial, right? So what I'm saying now is that, you know, if I match this certain property, then it's symmetric. So P implies Q, but now I'm saying Q or P is false. So this is always true. Yeah. Yeah. So yeah, properties, you need, in order to say that a property doesn't exist, you need a counterexample. If there's no counterexample, then yeah. So the empty set has a lot of properties, so to speak. All right. Yeah. Good question, though. Okay, so transitive. Sorry, I didn't really talk about this. So transitive, if I have elements X, Y, and Z in A, then for it to be transitive means if X and Y and Z are present as relations, then X and Z must also be present. X maps to Z. So that's a transitive relation. That just means that if I have this and this, I must also have this. Okay. So is equal to, is that transitive? Yes. Right. And for the same reason that we just saw, is it's vacuously true. So there is no, well, I mean, I guess you can map an element to itself twice. So it's not quite vacuously true. Yep, so that's transitive. What about is greater than? Yeah, is greater than is transitive. It holds. So if I say 2 is greater than 1, or say, say 4 is greater than 2 and 2 is greater than 1, and 4 is also greater than 1, right? As one example. So is greater than is also a transitive relationship. Is A divides B transitive? Yeah, it is. And we could do a little proof of that, but I'm probably not going to. I might do one at the end of class as an example, but yeah, if 2 divides 4 and 4 divides 16, then 2 is going to divide 16, for instance. Okay, so those are, so we have reflexive, we have symmetric, we have antisymmetric, and we have transitive. So those are the 4 main properties that we are going to concern ourselves with. So now we're going to talk about something related. Say we have a relation and we want to add one of these properties to the relation while adding as few elements as possible. So we call these closures. So what we're going to do is we're going to take a relation that is not reflexive, not symmetric, or not transitive, and we're going to make it into that as simply as we can. So for instance, is greater than is not reflexive. But if we wanted to make it reflexive, we need, of course, those guys. So we need all the is equal to relations. Right, so we need to add specifically, we're going to take our set builder notation in our original relation, and we're going to add these relations. So we're going to take the union of that set with this set of relations of every element mapping to itself. Right, and since they're sets, we can do that union, and then we can, of course, express it more simply just as A is greater than or equal to B. Okay, is that clear? So conceptually, I think it should be pretty clear. I just hope I didn't distract anybody with all the notation, but yeah. So we add these relations. So that's pretty, doing the reflexive closure is pretty simple. We're just going to add that set of self-mapping relations. Is greater than is not symmetric. So in order to make it symmetric, we want to add these opposite arrows, right? So if I have an arrow from 4 to 2, I also want one back from 2 to 4. So we're going to define this r to the -1. So it's the relation from B to A if the relation from A to B is in our original relation. Okay, so this is the inverse relation. So then the symmetric closure, we take the union of the original relation with its inverse. Right, so here I have the R is the relation A is greater than B, and here it's the relation that, did I write that correctly? A is, well, yeah, A is greater than B, but they're inverse now. So I guess I should have, anyway, it's correct, it just reads a little awkwardly. Right, so then it's the relation AB, A is greater than B, or A is less than B. So yeah, I should have written this differently. I should have written it as A less than B. Right, so then that just adds in those arrows. And I can use this, using the set builder notation, I just use the logical OR operator because we're adding in and we're taking the union. Okay, so symmetric closure. Any questions on that? So it's the relation R union the inverse. And yeah, we can, of course, write it more simply in this case. So now the transitive closure. So let's consider this relation. So we have it represented as a set, and we also have it represented as a graph. So in order to get the transitive closure, if I have, say, an arrow from 2 to 1 and an arrow from 1 to 3, then I need to add in this arrow from 2 to 3, right? And what else do I have here? So I have an arrow from 3 to 2, and I have an arrow from 2 to 1, so I need to add in this arrow from 3 to 1. All right, so we can identify all those. We can just take a look. So I have 1 to 3 and 3 to 2, so I need to add in 1, 2, and I have 1 to 4, but that leads nowhere. I have 2 to 1 and 1 to 3, so I need this 2, 3, and 3 to 2 and 2 to 1, so I need 3, 1, and 2 to 1 and 1 to 4, so I need 2, 4. So that looks good, right? Did I get them all? Yeah, it looks that way. Okay, so we can add these in. So we've added in these arrows. Is it transitive now? I mean, I think we're still missing. Yeah, it's not, eh? So we're still missing actually. So I have now an arrow from 3 to 2 but I've added this new arrow. So now I have this relation from 2 to 4, which means I need to have this arrow from 3 to 4. So in one step, we can identify some of the missing elements, but then that's going to introduce more missing elements, or it can introduce more missing elements, right? For instance. So yeah, so now we've added in this relation, and then I think it's transitive at this point. Looks that way. So notice that it took more than a single step. So we can sort of in one step identify some, but then those are going to introduce more possible relations. So for relation R, we can find transitive edges by composing R with itself, right? So that's essentially what we did back here. We mapped R to itself. So we mapped 1 to 3 and then 3 to 2, for instance. So that is R follows R. But we didn't find all the edges, of course. So in each step, we can find the transitive edges by composing R with itself and then taking the union of these transitive edges with the original relation. So yes, blue edges are R, purple edges are R squared, and the orange edge is R cubed. So then if I want to take get the transitive closure of R, I take R union R squared, R cubed in this case. Right, is that clear? Any questions? Okay, so how many times do we need to do this composition of relations in order to ensure that we have a transitive closure? So what's the worst case? Anybody want to take a guess? I'll be honest, I don't know exactly what it is, but I know one upper bound, let's say. As many times as there are elements, -1. Yeah, well, that's a good upper bound, and that's the one we're going with. So in this case, I would need log number of steps, right? So the number of extra edges, but this is a special case. So I was trying to come up with a bad example, but this was the worst I could come up with. But let's say that as an upper bound, we can take the cardinality of the set. We need that number of steps because there could be that many intermediate elements. But this is not not worst case. I don't know if maybe some of you can think about it and try and come up with a worse example. Maybe you can try and come up with an example that takes actually the cardinality of the set number of steps. I thought about it for a little bit and I didn't come up with anything, but you know, if yeah, something maybe to challenge yourself on and give a little bit of thought to. Does anybody have any ideas for that, or? All right, well, let me know if you do. So in general, for relation R on a set A, the transitive closure is simply the union of all the R union R squared, R cubed, up to R to the cardinality of the set. So if we do that, then we know for sure that we have the transitive closure. And it could be at some point, these relations all become equal to one another, but that's fine. We know that if we do this, we may have taken extra steps, but we will definitely have the transitive closure at that point. Okay. All right, so what happens if we compose a transitive relation with itself? What do we get as a result? So let's say T is a transitive relation on the set V. So what is T squared going to be? Or what can we say about T squared? T, maybe not. It might not be T. But what can we say about T squared? Is there a relationship between T and T squared that? So let's think about it then. If I have AB and BC, then the AC is going to be a member of T squared, right? So that just means I map from A to B, and then I map from B to C. So I get AC and T squared. But if T is transitive, then what do we know about T? Right? So if T is transitive, that means AC is already a member of T. So that means T squared is actually a this should actually be this shouldn't be a member, this should be subset. I'll have to remember to change that. So this is a subset of T, and in general, any T to any power is going to be a subset of T. All right. So that's sort of, if this property holds, then you know you have a transitive relationship. So good. Any questions on that? All right, so that's the end of this introduction to relations. So we're going to take our 10-minute break here. So it's 6:43. Let's say we'll come back at let's say 6:55, and then we'll look at sort of the more useful things you can do with these relations. All right, but that we'll take our break now. Okay, so we're back. So before we go to the next section, is there any questions on the previous material? All right. I am recording. All right, so now we're going to look at two basic types of relations, equivalence classes and partial orders. Again, this is based on the slides by Dr. Robert Collier, and I've made some modifications. So any mistakes you find are almost certainly mine. But yeah, we just looked at all the different properties. We looked at reflexivity, symmetry, anti-symmetry, and transitivity. And now we're going to see what those things mean, how we can apply them, and sort of some of the things that we can do with relations. All right, so we're going to look at two types. So a relation is an equivalence relation if it is reflexive, symmetric, and transitive. And a relation is called a partial order if it is reflexive, anti-symmetric, and transitive. And something we didn't talk about last time, so we talked about closures, we talked about reflexive closures, symmetric closures, and transitive closure. What about an anti-symmetric closure? Does that make any sense? So, or why? Let's think about, so anti-symmetric means not symmetric. Well, it doesn't mean not symmetric, but it means there's no symmetric elements except for what might be along the diagonal. So in order to have an anti-symmetric closure, so to speak, you would have to take away edges, right? So to make something that's not anti-symmetric into something that's symmetric, you would have to remove edges. So that's technically not a closure, so we don't talk about making things anti-symmetric that way. And then there's a question also of I have to remove one of these things, these relations that are symmetric. Which one do I remove? So it's not that simple a problem, or it's not as simple as making something reflexive, symmetric, or transitive. Anti-symmetric is something that basically has to exist beforehand. So we're going to start with equivalence relations. So equivalence relation, they're used to partition sets into disjoint subsets, basically around properties that we care about. And we're going to show you exactly how that works. So for instance, I give all you guys a grade, or you guys earn a grade, and I calculate it in Excel, and it's some number between 0 and 100. But then when you get your grade, you get one of these. You get an A plus, A minus, one of these, and that's it probably, right? At least that. But if you have anywhere over 90, so somebody might have a 92 and somebody else might have a 98, they both get an A plus. And so whether or not you have precisely the same mark, each student with an A has an equivalent mark. So that's sort of, you could think of these grades as equivalence classes of students and how they did in a course. So is this an equivalence relation? And it's not, of course, because it's not, it's not symmetric, it's not transitive, it's not reflexive. So how could we make this into an equivalence relation? So we have to add these properties. And of course we know how to do that, right? We can use closures. So we can take the reflexive closure, that's just simply mapping everything to itself. And then we can take the symmetric closure. That means that if I have a mapping, in this case, from F to H, then I must put one back from H to F. And then I can do the transitive closure, which means that, well, I have an edge from F to H to G, which means I need this one. And I'll also have, because it's symmetric, an edge from G to H to F. So I need an edge this way as well. So that's my transitive closure. So I do those three things, and now I have an equivalence relation. So what do we notice about this equivalence relation? Well, what do we notice? Should we do these closures in a specific order? Yeah, that's a very good question, actually, but I don't think so. So if I had done that in a different order, so the reflexive is obviously not going to affect anything, really. So the question is really whether we do symmetric and then transitive, or transitive and then symmetric. But at least in this example, and I can't think of an example where it would make a difference, but the fact that we did symmetric first means that both of these red edges are going to exist in transitive, because I know that really if I have F to H and H to G, then I know I have the other ones going back because it is symmetric. So I'm automatically going to get this symmetric transitive thing. And if I had done it in the other order, let's move back a bit. If I had first put in my transitive edges and then did my symmetric edges, well, now I'm still adding these back edges. So the answer is I am almost positive it won't make a difference. I cannot think of a situation where it would make a difference. I would have to confirm that, but I'm almost certain you'll end up with the same thing in both cases. All right. Yeah, so what do we notice? So these are, after we've applied all our closures, we get these complete directed pseudographs, right? So this is essentially the Cartesian product of A, C, and E. So I have every possible relation in this little subset of my graph, of my relation, right? And then the same is true for here. This is also the Cartesian product of H, G, and F. And this is the Cartesian product of B and D. So that means these have every possible relation, every relation possible. But there's absolutely no relations between subsets, right? So what we've done is we've sort of partitioned these sets. And these give us our classes. So we can make the equivalence relation using closures. Yeah. So I want you to hold on to this thought. So we're going to first, so this is how we can make an equivalence relation. We're going to show you now how we can prove that a relation is equivalent, is an equivalence relation, and then we'll go into sort of what this means. But what this means basically is I've partitioned my set into distinct classes. So this becomes one class of items. This becomes another class of items, similar to what we talked about with the grades before. So this might be, all my A students, and this is all the B students, etc. All right, so a relation is an equivalence relation if it's reflexive, symmetric, and transitive. So we have to prove all of those properties exist in a relation in order to prove that it's an equivalence relation. So let's prove, for instance, that the relation AB, where A is equal to B or A is equal to negative B, is an equivalence relation. So that means it divides it up into classes. So it's reflexive if for all of the X element of A, X maps to itself. So we can take universal instantiation. So now we're back to using proofs, which you guys should have seen many times before at this point. So we instantiate an element from our set A. So this from A. This element is equal to itself. And then we can do, now we do addition to say that since this is true, we can just add in this I is equal to negative I. So I equals I, or I equals negative I is true, since 2 is true. And then we can use universal generalization to get this property that these relations have, right? So either k is equal to k, or k is equal to negative k, which means that xx is in this relation. Yeah, that's right. Okay, everybody follow? That's stuff we've seen before, but we're combining things. So is there any questions on that? All right. So we want to prove now that it's symmetric. So we have this relation, so we want to say that, well, if xy is an element of R, then yx is an element of R. So we're going to use a direct proof. Since this is simply an implication, we can assume that this is true and use it to show that this is true. All right. So this is the sort of the definition of the relation. And then we're going to do a proof by cases. So we know that at least one of these must be true. So we're going to prove each one individually. So we're going to start with x equal to y. So if xy is an element of this relation R, that means that x equals to y is true in this case, case 1, which also means that y is equal to x because equals is, what is that, associative? Yes. And then we can do additive. So this is addition. Since we know y is equal to x, then we can just add this other proposition, which may or may not be true, but it doesn't matter. So then by this definition, yx is a member of this relation R, right? Since this is true, and this is an if and only if, then we can get that this is true. All right. Questions on that? So case 2 is if x is equal to negative y. So we're going to do the same thing. We have this member of the relation R, except that the implication is now that this part of it is true. So x is equal to negative y. Well, if that's the case, then y is equal to negative x. That's just math. And then we can do this additive step again, where we add in this y equals to x. Since we know this is true, this may or may not be true. It doesn't matter. So then yx is a member of R. So we've shown using case analysis that it is symmetric. Okay, good. Questions? All right. So the last thing we want to prove is that it's transitive. So what we're going to do again is, since transitivity is an implication, we're going to use the direct proof again. So we're going to assume that we have elements x, y, and y, z, and we're going to prove that that implies that x, z is a member. Okay. So how we're going to do that, now here's where it starts to expand a little bit, because we have this, again, we have this or definition. So we don't necessarily know which one of these is true, but we know one of them must be true for any member of this relation. So we have, this is our assumption. This is simplification. Yeah, this is the definition of R. We have this again as simplification. the definition of R. Okay, and then this is conjunction of 3 and 5. So we know that this is true. So now again, we're in this position where we're going to have to do some case analysis. All right, is everybody following so far? Is there any questions? Okay, so here's our final statement. This was fact 6. So how many ways can this be true? So this is in the form, we have a proposition P and Q that are mapped to x equal to y and x equal to negative y. And these two guys are mapped to these two guys. But how many ways can we make this statement true? So since this is a conjunction, we know that one of P and Q must be true and one of R and S must be true. So our different combinations are P is true and R is true. P is true and S is true. And Q is true and R is true, and Q is true and S is true. Right? So that makes sense. This is roughly, so if I put these values, I would have true or Q and true or S, right? And since this is going to evaluate to true and this is going to evaluate to true, this is going to be true and true. So if P is true and R is true, that'll make this true, right? So everybody's sort of following. So then if I substitute these back in for P and Q, then I have all my different cases these are all the different ways that this statement can possibly be true. So I have to prove each of these individually, right? And the proofs are relatively simple. So case 1, x equals to y and y equals to z. That means x equals y equals z. So x equals z, and then we can use, so all of this is math. And then this is addition. So that means that x and z is a member of our relation, which is what we wanted. So it's transitive in this case, if this happens to be true. If this happens to be true, well, x equals y equals negative z. That means that x is equal to negative z. And then we can do addition again. So this is addition. So that means x z is a member of this relation again in case 2. Right? And the other two cases basically follow the same sort of thing. So we have x equals negative y. So we've done a little bit of intermediate math here without writing it out expressly. So if we negate both of these, we get negative y is equal to negative z. So that means x is equal to negative z. We do addition, and we find again that xz is a member of this relation in this case. And then case 4. So again, we implicitly change the sign on these two numbers, these two variables, and so we get x is equal to z, and then we use addition again to complete our definition. All right, so that means R is transitive. Okay, so we've proven that this particular relation is reflexive, symmetric, and transitive using our formal proof methods that we learned earlier. So R is an equivalence relation. Right. Any questions? Everyone following? So if R is an equivalence relation on the set A, then the set of all elements related by R to A to little a in big A is called the equivalence class of little a. Right? So A is a member of A. So we can denote it with the square brackets and the subscript R for the relation, or just the square brackets if R is clear from the context. So that means if I write this, this represents a set of all the items that are equivalent from this relation. And any particular member of that set is called a representative of that class. Okay, and we'll see an example coming soon. So two equivalence classes are either disjoint, so they have no elements in common, or they're equal, so they have all elements in common. And we saw that sort of depicted in our graph earlier, where each class was sort of isolated on its own and there were no relationships between classes. So equivalence relations are used to categorize the elements of a set into equivalence classes. So yeah, and one sort of way to do this operationally is to grab a random element, find all the elements related to this and categorize them as class A, and then grab another uncategorized element and repeat. Right? So if it's an equivalence relation, you can just follow, I start at some element and I just follow the relations until I've seen everybody in that class. So for instance, here's a small set. So A has the same first name as B on the set, and these are professors and instructors in this department. So Anil Samayaji, Anil Maheshwari, Robert Biddle, Robert Collier, Jason Hynek. So for instance, the class with Robert Collier in it has Robert Collier and Robert Biddle. Right? So it's a set, and it's a set of all the equivalent elements in that class. So then another equivalence class would be the two Anils. I won't write their last names. And then a final equivalence class would be Jason. Okay. So does that make sense? So now these are partitioned into three separate subsets that don't overlap. They're either disjoint or they're completely equal. Yes, which is what I just said. So some of this is a little repetitive. So this is an equivalence relation. It's the one we saw earlier. Partition into equivalence classes, blah, 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 blah. Right. So this is stuff I've said, repeated it a bunch of times now. There's probably at least a couple too many slides in this this part of the slideshow, but so those are equivalence relations. Any questions on them? Yeah. So I guess the interesting thing to note is that when we talk about reflexive, symmetric, transitive, that we get these nice little complete graph subsets, which is, I don't know, that's kind of cool. All right. So the other application of relations, or one other application of relations, is partially ordered sets. So relation R on a set A is a partial ordering if it is reflexive, antisymmetric, and transitive. So we can call it a poset, which is a partially ordered set, and we denote it by the pair a tuple AR. So A is a set, and R is a relation on the set. So that's the that's the notation we use. So partial order can be used to specify an order or lack thereof of a set of events must occur in, right? So if I build a house, let's say building a house is a partial order, because first I have to build the foundation, no matter what. Then I have to build a frame. But at this point, I can do the plumbing and the wiring in any order. I could do one before the other. So these don't really have an ordering. We can't compare plumbing and wiring in terms of which should come first and which should come after, because it doesn't matter. But both plumbing and wiring must come before the walls, and wiring must come before light fixtures. So partial ordering is something where we can sort of put some things in order, but maybe not everything is relatable. Maybe not everything can be compared to each other, right? So relations are used as the comparisons, and it's often designated using this this notation, which is I'm not sure what it's called actually. I think it's predecessor something. Anyway, this is, so it's like a less than or equal to, but it's used to designate a relation in a partial ordering. So elements A, B of a post set. So this is one way to define a post set. Remember, we have a set S, and this is our relation. In this case, it's just a generic relation. So we're not giving any extra information here, but they're comparable if we can say that A compares to B or B compares to A. So that means that A, B, or B, A are in the relation. So otherwise, we could say A and B are incomparable. So what we talked about earlier, the plumbing and the wiring and building a house, those would be two incomparable elements. They don't really, one does not need to come before the other. And it's not always possible to compare two items. That's why we have the name partial order. All right, so we have less than or equal to on the set of integers. And we want to prove that that's a partial order. So again, we have to prove all of these elements, all these properties individually, the same as we did with the equivalence classes. So reflexivity, so we can do some universal instantiation. This is simply math. So that means that this is an element of the partial ordering. So this actually might be an incorrect way to write it. Yeah. So I'm gonna have to change this. This is not how we should write it. This is actually a member of the set less than or equal to, the relation less than or equal to. So yeah, that's not. Since a partial ordering is actually two sets. It's a set and then a relation on that set, which is another set. So yeah, I'll have to I'll fix those slides and re-release them. But yeah, you can see that anything we want to instantiate evaluates to true when we apply this relationship to it. So that means that this partial ordering is reflexive. So we need this anti-symmetry. So that means if these two elements are a member of this relation, then it must be that x is equal to y. So we have simplification. And this is definition of R. Simplification again. And again, definition of R. We do conjunction. And this, of course, if x is less than or equal to y and y is less than or equal to x, then it must be the case that x is equal to y. So this is an anti-symmetric partial ordering. Transitivity, again, so we're going to use a direct proof. So we're going to assume that this is true and then use it to show that this is true. So this is, again, simplification, definition, simplification, definition of our relation. And then the less than or equal to relation is actually transitive. So we get x is less than or equal to z. Right, which means that as a final step, I could have put this in, that this is in the relation. Right, so this is, this partial ordering is transitive. Okay, so that's how we would prove that a partial ordering is, or that a relation is a partial ordering. Any questions? So I have to fix up some of this notation. So some of this is used incorrectly, but yeah. All right, so since we know, since partial orders have all these properties, we can actually represent them more simply than we would a normal relation. So we have something called a Hasse diagram. I believe that's how you pronounce it, although I'm not sure. So we can start, so if we have this partial ordering on the set 1, 2, 3, 4, and the relation less than or equal to, we start with the complete Cartesian product, and then we identify all the less than relations, all the equal to relations. So this is our graph representation of this partial ordering. So can a partial order have a cycle? Right, so if I have 1, 2, 3, could this possibly be a partial ordering? And why or why not? So what would a cycle imply on a transitive relation? So what we'd have is that since this would be transitive, let's look at our little example here. Since I have this arrow from 1 to 2 and from 2 to 3, then I would also need this arrow from 1 to 3. And right now, I have a symmetry, right? And so then this is not anti-symmetric. If there is a cycle. So these are acyclic graphs. And because there's no cycles, they can be drawn sort of more simply than this. So a Hasse diagram is a graphical depiction of a partially ordered set where edges that are guaranteed to appear are not actually drawn. So which edges would be guaranteed to appear? So, well, we know that, for instance, we can remove the self loops. We can remove all the edges that must exist by transitivity. These are two types of edges that we know are going to be there. So we don't need to put them explicitly. It's just clutter. And then we can just order the initial elements vertically to indicate which way the relation goes. So for instance, if we take the Hasse diagram of this on these 4 elements, we start with the corresponding graph, remove the self loops, remove the transitive edges, and then place the initial elements below the terminal elements. Right. So this means all the relations that are missing are the arrows that go this way, and then our transitive arrows and the self loops. But since we know that all of those are there, we don't need them. So this is sort of a very simple depiction of a partial ordering. Right? Good. So let's look at a more complicated example. So let's look at this divides operator and the set of these numbers, 1, 2, 3, 4, 6, 8, and 12. So we're going to start with 1. So we know that 1, in a sense, divides everything. So instead of, so we showed you last time how to do, we could have taken sort of the complete Cartesian product of these in graph form, but we can also just build it up using our intuition. So we know that none of these divide 1, and 1 divides all of them, so 1 is going to be at the bottom. And then we're going to separate into 2 different paths here, because 2 and 3, 2 does not divide 3, and 3 does not divide 2. So 2 and 3 can't be related to one another. So these are going to be, the 1 divides them both. So 2 and 3 are not going to be connected on our Hasse diagram. And now we know that 2 divides 4 and 3 divides 6. But we also know, so we know that 4 divides 8 and 6 divides 12. But we also know that 2 divides 6 and 4 divides 12. Right. So do we think, are we okay with this? Is there any other edges that we think we need? All right. So there's a lot of information in this that's implicitly represented. For instance, we know that 1 divides everything because I have a path from 1, and by path I mean I'm always going upwards. So I can find a path from 1 to every element. So that means 1 divides everything. I know that 3 divides 6 and 12 because I know this transitive edge must exist. So as long as I can find a path from an element by only going upwards, then I know there's a relation. What I can't do is follow 3 to 6 and then from 6 down to 2, because 3 does not divide 2. So here I've gone down. So that's sort of an illegal move if I'm trying to get information from my Hasse diagram. Okay. We know 2 divides 4, 8, 6, and 12. So from 2, I can find a path from 6 to 12, from 4, and yeah. So from 2, there's multiple ways to reach 12. So there's a lot of information here, and we know that 8 and 12 don't divide anything because basically there's no upward edge from 8 or 12. Okay. Good. Any questions? Alrighty. So so these partial orderings also have a bunch of definitions that come in handy. So an item A is a maximal item if there's no B such that B is greater than A, so to speak, or B comes after A in the ordering, and A is not equal to B. So for instance, 8 and 12 are maximal items because there's nothing, in the sense, there's no upward flowing edges from 8 or 12. An item A is a minimal item if there is no B such that B is less than A, B not equal to A. So which one would be minimal on this? Or which ones? So here, simply 1 is minimal. Nothing else is. So because everything else has some edge going out downwards, so to speak. So if an item is maximal and can be compared to every other item, then it is the greatest item. So what do we mean by that? Well, in this case, there are no greatest items. However, if I put, say, for instance, 24, now everything in my Hasse diagram divides 24. So I could take any of these numbers, 2, 3, 6, 4, 8, 12. They're all factors of 24, or they're all divisors. No, factors, yeah. So then 24 could be the greatest item in this case. But in this particular Hasse diagram, there's no greatest item. Item is minimal if it can be compared to every other item. If an item is minimal and can be compared to every other item, then it's the least item. So in this case, 1 compares to everything, so 1 is the least. All right, so for a partially ordered set S and this relation and a subset of S, A, we can define an upper bound on A as some element greater than every element in our set A. Right, so for instance, what are the upper bounds on the set 1, 2, and 3? Anybody have, or what is one upper bound, we could say, on 1, 2, and 3? So there are multiple of them. So we could say 6 is an upper bound because 6 relates to 1, 2, and 3. We can say 12 is an upper bound because it relates to all 3 of them. 36 relates to all 3 of them. What about 4? Is that a valid upper bound? Or is it clear what I'm talking about? We're getting a little bit abstract here, but so in this case, 4 is not a valid upper bound because 4 does not relate to, in this case, 3. So 4 relates to 2 and it relates to 1, but it does not relate to 3. So 4 is not a valid upper bound. So 6, 12, 24, 36, these are all valid upper bounds on our set 1, 2, and 3. Upper bounds on 24 and 36, there's no upper bounds. Upper bounds on 6 and 8. So is there anything that relates to both 6 and 8 that's greater than both of them? 24, yep. So 24 would be our upper bound on both of these numbers. So that's sort of, that's how these partial orderings work, is that sometimes you can compare items and sometimes you can't. Again, for a partially ordered set S and a subset A of S, if we have a set, an element that's less than or equal to every member of a subset of S, then L is called a lower bound of A. So this is just, so a lower bound on 1, 2, 3 would be what? Something that relates to all of them, but is at least as yeah, 1. 1 would be the lower bound. Lower bounds on 4 and 6. So again, we need numbers that relate to both 4 and 6, but that are less than 4 and 6, or less than or equal to. But they have to be less than or equal to both of them. So I guess 2 would be a valid lower bound because it relates to 4 and 6. And then 1 also relates to both 4 and 6. 3 relates to 6, but it does not relate to 4, so we can't use 3. So 2 and 1 are the 2 lower bounds. Lower bounds on 24 and 36. So it has to relate to both of them. So we can, all of these relate to both of those numbers, and they're all less than or equal to them. Does the descending numerical order matter? I'm not sure. What do you mean by that? I think in this case, it's just, if I understand you correctly, it's just a product of the, for the lower bound 2, 1. Oh, no. Yeah, these are just, yeah, the order doesn't matter here. So this is not a set. Each of these individually is a lower bound on this set. But yeah, the order doesn't matter. They're just two separate elements. All right. Sometimes we want a valid linear order. So we can use topological sorting to obtain an order that by repeatedly taking the minimal item. So for instance, if we are building a house and there is a partial order to building a house, but there's only one person or one group of people, so we can only do one task at a time, then we want some sort of ordering where we can do some valid ordering. And so to get that, we can repeatedly take the minimal item. So in this case, 1 is the minimal item. So that's going to be the first thing that we have to do. But now we have 2 minimal items, so we can take either one of these. So let's take 3 in this case. Now we have a least item because it does relate to everyone here and it is minimal. So we need to take 2 in this case. And then again, we can take either 4 or 6. So let's take 4. And now we have 8 does not relate to 6 or 12. So we can take 8 if we wanted to, and then 6 and then 12. And that gives us a valid ordering by topological sorting, right? Other orders are possible. Basically any order that doesn't violate the partial order, but I could have taken this or this. Either of those would work too. Okay, so that's equivalence relations and partial orders. So it looks like we are done a little bit early, except that I will stick around and do, well, one other thing actually. So a couple of uses of these partial orderings that I did talk about, but that's essentially all the, I'm going to do a few examples here and maybe expand on these topics a little bit. But in terms of the content, that's the technical content, that's all finished now. So, you know. However, we could talk about a couple applications of these partial orderings. So for instance, so if I want to build a video game, then you know, in the beginning, I choose my platform. That has to be done first. I choose the type of game. And then I can choose over here a physics engine, if it's a, you know, physics-based game. Enemy AI, which depends on the physics engine. And over, whoops. All right. So let me redo that very quickly. So, and then, yeah, if I make the models over here, and then I make textures, and then play test, and let's assume that I didn't erase all this stuff, then, you know, I can assign a team after I've done these 2 tasks, then I can assign, you know, team 1 to do this, this path, and team 2 to do the other path. The other thing this is good for is if I have some partial order, perhaps multiple paths, I can do parallel programming on these paths. So I can take some multi-core processor and then I can assign task 1 to one processor, task 2 to another one, et cetera, et cetera. So these are some of the usefuls topological sorting. Or not topological sorting, but partial orders. Okay. I'll do, yeah, that's basically it. I'm going to do one more example of a partial ordering. And then that'll be it for tonight. So let's see here. So if I take, say, a partial ordering, which is the power set of A, B, and C, and the relationship is subset. So this is a partial ordering power set. So at the top, I have the complete set, and then at the bottom, I have the empty set. So the empty set is, we know, is a member of all subsets. And since we're doing the power sets, then all the sets in the power set are a subset of the original set. So this would be a greatest element, and this would be a least in this case. And then, so to start with, we have all the sort of one-member subsets, so A, B, and C. And that's a subset of them. And then at the next level, we have all the two-member subsets. So we have AC, A, B, and BC. And then, of course, at the top, we have the three-member subsets. So those two guys map to him. Oh, did I draw this wrong? Sorry. I'm going to actually draw C here and B here. So B goes here, C goes there. Right, and we get sort of this nice little implicit cube, and this is the partial ordering using a power set and a subset. And that's, yeah, so we can see that it's not, we can have sort of paths that diverge and then converge again, right? So I have a path here that goes to A and then converges again. So A and B are not comparable, but they're both subsets of the common set AB. So yeah, that's just another example. Yeah, any questions? All right, well, that's it for tonight's class. It'll be a bit shorter, but a lot of that relations is heavy material, so it's probably a good thing. I'll stick around for the next 10 minutes for questions, but other than that, yeah, that's it for tonight.